Welcome again. Okay, so we are done with the general stress transformation. Okay, so now we are going to discuss. Okay, where's my ball pen again? It's disappeared. Okay, so let's erase this one. Okay, I prefer to use the black color pen. Okay, so right now we are going to discuss the principal. Okay, the principal stresses. The principal stresses and maximum max, okay, maximum in plane, of course in plane, because we are dealing with in plane. We are dealing with an element on an in plane, on a plane, okay, in plane shear stress, shear stress. Okay, before we discuss in detail, so let's clearly understand the physical meaning of the important keyword. Okay, so the important keywords are the principal stress, this one, and the maximum in plane shear stress. Okay, so what is principal stress? Okay, so recall our equation. Okay, so the new value for sigma x prime or sigma y prime will change accordingly due to the rotation of theta. Okay, so that means for different value of theta, we are going to have different value of sigma x and sigma y. So right now, our concern is we want to determine the principal stress. Okay, so this principal stress is referring to the minimum or maximum value of normal stresses. Okay, and then at the same time, we do not know, okay, at which angle, at which theta, the stress is maximum. Okay, so that is the general physical meaning for principal stress. Okay, and then similarly for shear stress, okay, so we know that the new value for tau xy prime will change, okay, with respect to the changing value of theta. Okay, our concern is the maximum in plane shear stress. Okay, and then in order to determine the value for maximum in plane shear stress, we need to define the respective theta. So at what theta will give the maximum in plane shear stress. Okay, so first, let's discuss in plane principal stress. Okay, so what happened? Okay. In plane principal stress. Okay, in plane principal stress. Okay, so let's circle this in plane principal stress. Okay, so recall our modern maths during high school or maybe during the secondary school. Okay, so we learn quadratic function. So let's say we have a quadratic function with respect to the x-axis and y-axis like this. At this point, the value is maximum. Okay, so what other property that we can have on this point? Okay, so the slope or the differentiation of the dy dx, okay, dy dx is equal to 0. Okay, so at this point, at this maximum point, the dy dx is equal to 0. Okay, and then similarly, in order to determine the in-plane principal stress, so we have to differentiate the function. Okay, so recall your favorite equation. Okay, so your favorite equation, okay, the new sigma x prime is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cosine 2 theta plus tau xy sine 2 theta. Okay, so our objective is to determine the maximum value for this normal stress. Okay, so in order to determine the principal stress, so we need to differentiate our favorite equation. So this is your first equation. Okay, so we need to differentiate with respect to the theta because we want to know at what angle, okay, what is the value of the angle that will give the maximum value or the minimum value of normal stress. Okay, so let's differentiate our first equation. Okay, d theta, okay, d theta is equal to minus sigma x minus sigma y divided by 2, okay, 2 sine, okay, you need to apply the chain rule, 2 sine 2 theta plus 2 tau xy cosine 2 theta. Okay, so we know that the solution for this derivative equation is equal to 0. So the next step is we just need to rearrange this equation. Okay, so we have the negative portion, just shift this portion to the left. Okay, and then this portion remain here. So you will get the positive value. So after rearranging the equation, you will get this final equation. Okay, so tangent 2 theta. Okay, so we denote 2 theta p because we want to determine the principal. Okay, the principal theta that will contribute to the value for the principal stress. Okay, so let's define the equation as tangent 2 theta p is equal to tau xy divided by sigma x minus sigma y over 2. So this is the important equation in order to determine the principal stress. So you have to memorize this equation, okay, in order to determine the principal stress. Okay, so other method to memorize this equation, okay, if you look at this equation, you can draw a diagram. Okay, so let's draw a diagram. Okay, so tangent to theta p, so let's define x-axis. Okay, x-axis. Okay, and our x is our normal stress, and then make sure so our y is our shear stress. Okay, by having these by having this tangent to theta p, so you can define like this. Okay, so let's use this red color. So we draw a line here. Okay, so this is your 2 theta p. Okay, by having this equation, so we know that so the length here, okay, the length here is equal to sigma x minus sigma y divided by 2. Okay, and then the height here is your shear stress tau xy. So that we will get this equation. Tangent 2 theta p is equal to tau xy divided by sigma x minus sigma y over 2. So this is the value for, this is how we express the trigonometric properties of this equation. Okay, and then the most important part is that this theta p, okay, the solution for this theta p, we are going to have two solutions for this theta p. So that means other angle is from the can be defined from this side. Okay, so this is your first 2 theta p1. Okay, the second one is defined from here to here. So this is your second theta p. So this is your 2 theta p2. Okay, and then similarly, since it is on the left side, so the distance here is equal to sigma x minus sigma y divided by 2. Okay, and then the height here is in the opposite sign is equal to minus tau xy. So this is one of other method in order to memorize this equation. Okay, by right we can also use this diagram in order to determine the principles, in order to determine the maximum in plane shear stress. So for now, let's focus on this principle, normal stress. Okay, since we are going to have two different value for theta p and theta p1 and theta p2, so we are going to have two different value for principal stress. Okay, so we denote the principal stress as sigma 1 and sigma 2. So either one will be maximum or minimum. So the equation is equal to, okay, sigma x plus sigma y divided by 2 plus minus this hypotenuse. Okay, so this hypotenuse. Okay, so this hypotenuse, okay, which is equal to the square root, okay, square root, okay, sigma x minus sigma y divided by 2 square, okay, square plus tau xy square. Okay, so this is what we call the hypotenuse. Okay, let's use other color. Okay, let's erase this one. Where's my eraser? Okay, let's erase this symbol. Okay, to make sure you clearly understand. So use red color. So this is the hypotenuse. Okay, hypotenuse of our diagram. Okay, hypotenuse. Okay, this length. Okay, and this part is the average normal stress. So this is our next important equation. So for now we have two different equations. So this equation can be used to determine the angle that contribute to the maximum principal stress. Okay, and then this equation can be used to determine the principal stresses. Okay, the maximum and minimum principal stress. So there is no theta here. So we can simply determine the value without calculating the theta. Okay, next. Okay, welcome again. Okay, so the objective of our lecture just now is we want to determine the again my black pen here. Okay, my black pen. Okay, maximum in we are going to determine the principal stress. Okay, eraser. Okay, erase again. Okay, so we want to determine the principal stresses and maximum in plane, of course in plane, maximum shear stress. Okay, maximum in plane shear stress. Okay, so we are done with the principal stress. Okay, so we skip the detailed derivation. Okay, similarly to our previous lecture, so we need to define the theta in order to determine what kind of theta, what is the value for theta that will contribute, okay, that will result in the maximum value of normal stresses or principal stress. Okay, so for maximum in plane shear stress, okay, so the theta, so instead of theta p, since we want to determine the shear stress, okay, so we state the theta as theta s. Okay, before this, we have theta p, and now we have theta s. Okay, so this can be expressed by using this equation. Again, tangent to theta s is equal to minus, okay, again, sigma x minus sigma y divided by 2 over tau xy. Okay, so you need to memorize this equation. Okay, congratulations. Okay, so it seems that we have a number of equations that we need to be very familiar. Okay, one step, and then we have to memorize all these equations. Okay, by right, okay, so we can express this equation or the diagram, okay, similarly as what we did just now. Okay, so let's draw a diagram. Okay, so the x-axis is your normal stress, the y-axis is your shear stress. So we want to express this tangent to theta s. Okay, so let's make the notation clearly. So the s must be written smaller than theta. Okay, so that you will not get confused later. Okay, so this tangent to theta s can be expressed like this. Okay, be careful, since we are referring to the shear, so we are referring to the shear axis, tau axis. Okay, so the angle can be defined like this. Okay, so we draw a straight line like this. Okay, and then this is your theta, 2 theta s. Okay, so this 2 theta s, okay, so you can refer to this equation. Okay, tangent 2 theta s, so the height here is positive tau xy. Okay, and then the length here, the horizontal length is equal to minus, okay, be careful, minus sigma x minus sigma y, okay, divided by 2, oh sorry, um, Correct. Okay, correct. Okay. Okay. And then as we discussed before, we are going to have two solutions for this theta s. Okay. So the next solution for this theta s is from here. Okay. The theta s, okay, is defined from this positive shear stress to here. Okay. So this is your 2 theta s1 and this one is your 2 theta s2. Okay. Okay. So this is how can we determine the maximum in-plane shear stress. Okay. If for principal stress, you have the equation to determine the value for the principal stress. Okay. Similarly, for maximum shear stress, okay, so the equation is equal to the maximum in-plane shear stress, okay, can be calculated by having the hypotenuse. Okay, by having the hypotenuse. Okay, so just simply take the equation to for the hypotenuse. Okay, so sigma x minus sigma y divided by 2. Okay, don't forget the square bracket plus tau xy square. Okay, so the value of the maximum in-plane shear stress. Okay, and then so again recall our average. Okay, so we have average normal stress. What we don't have average shear stress. Okay, the average for normal stress is equal to sigma x plus sigma y divided by 2. Okay, so please take note this equation. Okay, so we will discuss an example after this. Okay, so until now we have discussed some of the theoretical background on, okay, right, again on the principal stresses and maximum in plane shear stress. Okay, in plane shear stress. Okay, so let's discuss an example. Okay, as an example. Okay. Okay, let's say you are given an element. Okay, so this is your element. Okay, so this is the initial state of the element. Okay, and then the normal stress is, let's draw the normal stress. So the normal stress here upward is equal to sigma y. Okay, so this is your normal stress. So we just take the number. So ignore this one. Okay, so this here is 90 megapascal. Okay, and then we have inward normal stress, which is equal to 20 megapascal. Okay, 20 megapascal. Okay, and then we have a positive shear stress. Okay, positive shear stress, which is equal to 60 megapascal. Okay, so let's define the parameter. Okay, so by referring to this diagram, your sigma x is equal to minus 20 megapascal. Why minus? Because the direction of the normal stress is inward to the plane, to this plane. Okay, and then your sigma y is equal to 90 megapascal. Okay, and then your shear stress, okay, positive sign shear stress is equal to 60 megapascal. Okay, so the question is, okay, determine the first one, the principal stress. Okay, the principal stress, and then determine the maximum in plane shear stress. In plane shear stress. Okay, let's determine the principal stress. Okay, first we need to determine the, okay, our first step, we need to know the orientation. The orientation of the element. Okay, of the element. Okay, so this is our first step. Okay, first step. Okay, in order to determine the orientation, you need to have the theta p. Okay, theta p. So recall your favorite equation. Okay, so you know that tangent to theta p is equal to tau xy divided by sigma x minus sigma y, okay, divided by 2, okay. So you will get the value for theta, okay. You will get two value of theta. So the first one, 2 theta p is equal to minus 47.49 degree, okay. And then the second one is 2 theta p is equal to 66.3 degree. So let's just simply define. So this will be your 2 theta p2, 2 theta p2, and this one is your 2 theta p1. The first 2 theta p, and this one is the second 2 theta p. Okay, and our concern is the theta. So that means your theta p2 here is equal to minus 23.7 degree. So that means the rotation is in counterclockwise direction. Okay, and then the second theta P1 is equal to 66.3 degrees. So we have two different value. Okay, so that is our first step. So we have the angle. Okay, and then the next step, we can also draw the diagram. Okay, so we can also draw the orientation of the element. Okay, so we know that. Okay, let's just have this value. Okay, your theta is equal to 23.7 degree. So this is your original axis, xy axis. Okay, so the new orientation of the axis by having theta equal to minus 23.7 degree is like this. So this is your new x prime. Okay, and this one is your new y prime. So I will use red color, okay, to avoid confusion. So this is your new xy prime. Okay, and this is your new y prime. Okay, so we can draw our element. Okay, the orientation of our element will be like this. So this is the orientation of our element. Okay, so our job right now, okay, our task right now is to determine the principal normal stress, which is perpendicular to this plane. Okay, and then the other one. So we have two different value, sigma x or sigma y. Okay, but we can just simply use our equation before. So we know that the maximum or the principal stresses, okay, either maximum or minimum, can be calculated using this equation, which is equal to sigma x plus sigma y, okay, divided by 2. So take note here. So this is the average normal stress. Okay, the average normal stress. Okay, and then we need to include the hypotenuse. Okay, so positive minus, so the hypotenuse, sigma x minus sigma y over 2, don't forget the square, plus tau xy square, and then square root. Okay, since we have positive and minus sign, you are going to have two different value for normal stress. Okay, so your sigma, the principal stress, okay, is equal to 116 megapascal, 116 megapascal. Okay, and then the second one is equal to minus 46.4 megapascal. Okay, let's erase this one. Okay, erase this one to avoid confusion. Okay, so and then let's highlight the answer for this calculation. So we have these two value. So from here we know that sigma 1 is the maximum principal stress. Okay, and then sigma 2 is the minimum principal stress. Okay, we can just simply refer to the signs. So right now what we need to do is, okay, we do not know this 116 megapascal is the value for normal stress at this position or at this position. So we have to check. Okay, so back to our angle. So we know that for value minus 23.7 degree. Okay, so this is your angle. Okay, downward. Okay, downward 23.7 degree. So this is the angle. Oh, sorry. Eraser, delete these lines. Let's draw the line carefully. Make sure it is a straight line. Okay, so this is your straight line. Okay, and then this is your theta, which is equal to 23.7 degree. 23.7 degree. So we want to check. Okay, this angle will contribute to this maximum 116 megapascal, or it will contribute to the minimum minus 46.4 megapascal. So we need to check. So what we can do is, okay, so we can use our very first equation. Okay, so we know that. So let's say this is your x prime axis. Okay, x prime axis. So the new sigma x prime is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cosine 2 theta plus tau xy sine 2 theta. So we just simply substitute this angle. So make sure the sign for this angle is in negative sign. So the theta here is minus 23.7. Okay, and then sigma x, we know sigma x is equal to minus 20. Okay, sigma x. Okay, where's my red color? So this is your sigma x. Okay, your sigma x. And then your sigma y, this is your sigma y. And then your initial state for shear stress xy, this is your initial state for your sigma stress. Shear stress. Okay, so in the end you will get the value is equal to minus 46.4 megapascal. So what does that mean? So this angle theta, okay, minus 23.7 will contribute to the minimum stress, okay, the principal stress, which is equal to minus 46.4. So that means the normal stress here is in inward direction, okay, which is equal to 46.4 megapascal. Okay, and then similarly we can do the same thing for sigma 1. Okay, so we check the angle. No need to check because we know already. So automatically we know that the other normal stress is in positive sign, sigma 1, which is equal to 116 megapascal. So this is the orientation of the this is the orientation of the element after being rotated with theta equal to 23.7 degree. And then this value, these two values are the principal stresses. Okay, next we are going to discuss the maximum in plane shear stress. Okay, again we just need to determine the value of theta s. Okay, and then draw the orientation of the element. Okay, so now we are going to determine the maximum. I prefer to use the black color. So erase this one. Okay, black color. Maximum in plane shear stress. Okay, shear stress. Okay, so let's determine the maximum in plane shear stress. Okay, we just use the same example. So let's say this is your initial state of our element. Okay, same value. So the normal stress, so this here is 90 megapascal, here inward 20 megapascal. Okay, and then the shear stress, okay, which is in positive sign, is equal to 60 megapascal. Okay, so just to avoid any confusion, so I stated the value for each parameter. Your sigma x is equal to minus 20 megapascal, and then your sigma y is equal to 90 megapascal. Okay, and your shear stress tau xy is equal to 60 megapascal. Okay, so the problem here, we want to determine the maximum in plane shear stress. Okay, so recall our first step. Okay, as we did just now, our first step is we need to determine, okay, to identify the orientation of the element. Okay, so in order to determine the orientation of the element, we need to get the theta. What kind of theta? Theta S, because we want to determine the maximum in plane shear stress. So recall again your favorite equation. So tangent to theta s is equal to minus, okay, sigma x minus sigma y divided by 2, divided by tau xy. Okay, so you will get two different answer. Okay, the solution for this 2 theta s. So the first one, 2 theta s is equal to 42.5 degree. Okay, or your theta can just simply equal to 21.3 degree. Okay, and then the other solution for this 2 theta s, okay, is equal to 180 degrees. So in the same calculation, if we refer to the diagram, plus 2 theta s1 here. Okay, either one is same. Okay, so that means your theta s2 is equal to 111.3 degree. Okay, so this is your angle. Okay, so we know that this is your maximum theta s. Okay, not maximum theta s. So this is the theta s which contribute to the maximum in plane shear stress. So now we can determine the maximum in plane shear stress, okay, by having this equation. Okay, maximum tau maximum, okay, is equal to the hypotenuse sigma x minus sigma y, okay, divided by 2, okay, square bracket plus tau xy square root, which is equal to plus minus, okay, plus minus because we have the square root, okay, is equal to 81.4 megapascal. So we are almost done with the calculation. So the next step, we just simply draw the orientation of the element. Okay, so again, so let's say we refer to this angle 21.3 degree. Okay, so let's say this is your original position of your x-axis. Okay, 21.3 degree is in positive sign. So that means the rotation will be like this. So this will be your new x-axis. Okay, x-axis and y-axis. Okay, so we can draw the orientation of our element. Okay, will be like this. Okay, so this one like this. Okay, and then don't forget to state the angle. Okay, the angle here. So here is your reference axis. Okay, the angle here is 21.3 degree. Okay, and then based on our calculation, okay, we have positive minus 81.4 degree, 81.4 megapascal. So we have two value. So we do not know which one that is defined from this 21.3 degree. So we need to check. So how can we check? So we can use this equation. Okay, so recall our very first equation for new xy prime. Okay, is equal to, okay, minus sigma x minus sigma y divided by 2 sine 2 theta plus tau xy cosine 2 theta. Okay, so just simply substitute this angle. Okay, this angle, this 21.3 degree, substitute in this theta. Okay, and then sigma x, sigma y, you just take this value. Just substitute the value, then you will get the solution for the new shear stress is equal to 81.4 megapascal. So notice here we have a positive sign. So we have a positive sign. So that means, okay, the orientation of the shear stress is like this. So this is your shear stress. Okay, 81.4 megapascal. Okay, and then this is your the other part. In this end, okay, so I just okay, that's all. So this one, the same, of course, same value. Tau xy is equal to tau yx. So we are done with our calculation. Okay, so in your solution, okay, when you try to solve this problem, so make sure you be careful with the positive and negative sign. Okay, and then draw the orientation of the element. So we are done with the normal stress. The principal we are done with the stress transformation. Okay, the principal normal stresses and the maximum in plane shear stress. Okay, see you again.